One of our favorite tricks for finding new math is to take a idea in math that we're familiar with, that we're comfortable with, that we know well, and in some way extend it, generalize it, so that it applies in some larger space, in some larger way. Okay? That's what we're doing in this section. It's actually what we've been doing for most of this chapter. All right? So let's say we have a linear transformation. Linear transformation t from Rn to Rm. Now, since t is a linear transformation, and since its domain is Rn, and its codomain is Rm, we know t is a matrix transformation. And so it has a standard matrix associated with it. T has a standard matrix. Let's see, let's call it M sub t associated with it. Okay, and the idea here is that if I want to take the transformation of a vector x, that's the same as multiplying matrix T by vector x. Okay? And actually, in the special case of matrix transformations, this matrix tells us an awful lot. And there's a very strong relationship between the transformation and the standard matrix of the transformation. Okay? For example, in the last section, we saw that for matrix composition, if I have two linear transformations, S and T, I think I want to swap these around. Okay, so if I have two linear transformations S and T, and they have associated standard matrices M sub S and M sub T, then the composition of the transformation, the standard matrix of the composition is just the product of the matrices. Okay, so composition of transformations is very similar to matrix multiplication. There's an analogy here, right? Similarly for inverses. So if we look at the inverses of transformations, if T inverse is the inverse transformation of a linear transformation T, then the standard matrix of the inverse transformation is the inverse matrix of the original transformation. Okay? This is the standard matrix of the inverse transformation. And so the functional inverse of transformation T is analogous to the multiplicative inverse of the standard matrix of T, M of sub T. Okay, so there's this relationship here. It seems like that a transformation T is more or less the same thing as its matrix M sub T. They have the same information. They carry the same information. They just carry that information in different ways. Okay? But we can use transformations, linear transformations, where a standard matrix won't work. What do I mean? So a linear transformation only is guaranteed to have a standard matrix associated with it when the domain of the transformation is a vector space like Rn. Okay? R, set of all real numbers to a certain number of dimensions. Okay? But linear transformations can apply to more spaces than that. So, if we have a transformation from a vector space V to a vector space W, it might not have a standard matrix associated with it. May not have a standard matrix associated with it. But we saw up here, when it does, it behaves a lot like a matrix, right? When the transformation has a standard matrix associated with it, it behaves a lot like a matrix. So we can extend the ideas of matrices to places where a matrix may not make sense by thinking of linear transformations. We can think of linear transformations generally actually, let me say of a linear transformation. Let's use the singular. We can think of a linear transformation as a sort of generalized matrix. So even when a matrix won't work, linear transformations may. And it turns out a lot of the properties that we are familiar with matrices can be applied to linear transformations. In this section, we will explore some of these.